questions at all about the class? You guys all saw my announcement that I sent on Canvas, right? I think several of you have already filled out the poll. I forgot to mention in that announcement when the poll will close. Let's say 24 hours from now. Okay, and I'll send out an announcement again to remind people about that. Just staring at the responses real quick, it's probably going to be on an evening at some point. So I will point out that in previous years, under normal circumstances, the exam is usually scheduled at like 7 p.m. on a Wednesday or something like that, and you would have 2 hours, and so this is somewhat more normal. How do people feel about just taking the exam at home, or would people prefer some sort of space? Like, are people able to, is everyone able to have a quiet space at home to do stuff, or do you have really loud neighbors or whatever? Please contact me if that's not the case, okay? And we'll try and figure out something. Questions at all about how the exam will run?
Will there be like so this is just going to be like, hey, we're going to print out the questions, or like do it on pen and paper and then scan it and then upload it during the
Yeah, I'm assuming, at least I'm old-fashioned enough to think that pen and paper is still just more reliable than either writing on a tablet or like doing something online or something like that. And so my hope is that what you guys will do is you can probably just keep it as a PDF if you wanted to, but you could also print out the exam, and then I will ask that all of you have just write all the solutions down, or all your solutions down on 8.5 by 11 inch paper, like standard white paper, and then scan it or take very high quality pictures and then upload those as PDFs. And I'll have instructions all about that as it comes up.
And like, I understand that the exam is open note, but is it also open book?
Yes, open all materials to this class, including the notes that that I've been posting online.
Okay.
Okay.
Is there going to be like an equation sheet additionally, though, given that we should like print out with it, or certain resources recommended?
No equation sheet. The equation sheet is basically just all of your notes. If it were a closed note exam, then I would give you an equation sheet, but you know, you have basically all of the notes in front of you for this. What I was going to say, we're likely going to do some sort of review session. We're probably going to turn the office hours of that exam week into some sort of review or something like that, just letting you guys know. And then, of course, you know, come to our office, come to my office hours, come to, you know, the TA's office hours and stuff, and we'll try to help you as much as you can to prepare. Okay. But that's still a couple weeks ahead. I think the more pressing thing for most of you guys is the kinetics exam, so I'll let you guys stress out about that before you worry about my class. Okay. But for now, let me go ahead and continue with the material that we've been covering. We spent several lectures at this point talking about FFT. That's this finite Fourier transform method that allowed us to solve differential equations, basically. So the first method that we had for solving differential equations was called the similarity solution. But now if we have this sort of scenario with very well-defined boundary conditions all in the finite domain, then the way to do it is to use this FFT method, right? And you know, we've walked through just one quick example of this. I've talked you through both the overall strategy, which we'll go through today in another example. Basically, you express everything as a sum of basis functions, you transform the PDE and the boundary conditions, and then you solve, and then that transforms it into an ODE with boundary conditions, and you solve. And then you end up with a problem you end up with a solution that's sort of a sum of several different solutions and stuff. Okay. We also talked a little bit about the basis functions and because as we mentioned last time, the basis functions are sort of the magic of how this whole method works. And so I'll talk a little bit more about those in a more fundamental aspect a little bit later on in the class.
I just realized another question over the exam. When we're having, I would assume that there should be a question over like similarity transformations. Like on the exam, will you provide us like the similarity variable we're using, or do we have to just like come up with one?
I'm not sure. I haven't written the exam yet. So yeah, let me get back to that later. Okay.
Sorry for the interruption.
Yeah. So I don't remember where I was now. We were talking about basis functions of, yeah. So anyway, you guys have figured out basically at this point how to do one FFT example. I'll do one more. The first 3 problems on the homework are basically just classical FFT examples that you guys should be able to do. Might have been able to do already, like at the beginning of this lecture, but by the end of this lecture, definitely you'll have all the material that you'll need. As I mentioned in the announcement, the last problem will require some stuff that will preview a little bit today, but definitely cover on Monday. Okay. And so for now, let me just go ahead and walk through this FFT thing with one more example. Okay, so let's just say another example. Okay, and this example is actually something that, it's not even a new example, it's just something that we've actually already covered. But the solution will basically illuminate us again on how to actually do this problem. Okay, so the example is basically our original problem. Okay, our original problem looked like this. And I'm skipping all the non-dimensionalization and all that sort of stuff because we've already seen it before and it's all exactly the same, right? Basically, this was the plate between, or the fluid between 2 plates initially at rest at time t equals 0. The bottom plate is pulled to the right at a speed of u. And throughout the entire experiment, the top plate is held steady. So we have no slip boundary conditions at 0 and 1, or 0 and h non-dimensionalized and stuff like that, right? And so before, I'll say previous solution, the way that we did that before was break up into steady state and transient pieces, right? If this is not ringing a bell, what we did was we expressed our solution in terms of that, right? If you recall, our solution looks something like f of y of t equals 1 minus y. And the reason why we picked 1 minus y is because 1 minus y is what you should get eventually at steady state. In other words, you took this original equation, you set the time derivative equal to 0, and then you satisfied the boundary conditions at y equals 0 and y equals 1. And that gave us 1 minus y, okay? And then when we subtracted this from our original problem, then we get the same PDE with a different initial condition, but 0 boundary conditions, and that made it a little bit easier for us to go through the FFT solution for, okay? What we're gonna do today is not this method. We're just going to solve directly for f. Okay. One of you guys, I think, actually asked about this, whether you can actually do it. Well, that's essentially what we're going to do. So if you recall, the FFT solution had 4 steps. The first step is to express the solution as a sum of basis functions. Okay. And the basis functions in this case, well, let me go ahead and first express that solution as a sum, and then I'll talk about the basis functions in just a second. So it's an infinite sum. And then, of course, that implies then that the inner product can be used to determine what the coefficients are. Right? Or, this is basically the definition of the inner product. Right? Now, the basis functions, remember, were sort of the magic of how this whole thing worked. The way that we determined the basis functions for the previous problem was we solved an equation that looked like this, right? Because as we recall, the basis functions have to satisfy an eigenvalue problem that has the same operator as our particular problem. But our particular PDE is the same PDE as before, and it has the same boundary conditions as before too, or at least it has boundary conditions of the same type as our previous solution, right? Type meaning that the boundary conditions were that G previously, but now F is equal to something at y equals 0 or y equals 1, as opposed to the derivative of G, the derivative of F is equal to something. And so it's essentially the same problem for the basis functions, and so it should be the same basis functions. Just to remind you, this is how we found the basis functions basically. We take the differential operator in the FFT variable, so in this case y, and then we solve the eigenvalue problem for that. That gives us a second order differential equation with two boundary conditions that are the same type as what we have. And so in this case, it will be phi equals 0 and phi equals 0 at y equals 0 and y equals 1. Okay, and then that gave us infinitely many solutions. Okay, once we had those infinitely many solutions, we plugged in the boundary condition. We plugged in the boundary conditions, and then that's basically what gave us this. And then to find an, we normalized it by making sure that everything is orthonormal. Okay. And so we can go through all that exact same thing, but it would, like I said, give you exactly the same thing. But the basis functions in this case should therefore be the same. Sorry. And just to remind you, if you are not so fortunate where you've actually seen this exact same problem before and know exactly what the basis functions are, you can go through this process to determine the basis functions where you solve this differential equation and plug in the boundary conditions. Or you can also just go in the textbook and then look up what the basis functions would be for the actual problem that you're looking at. Okay. Okay, so in this case, the basis functions are that. The reason is because the PDE is the same. And we still have, this is boundary conditions of the same type. These are called Dirichlet conditions. Okay. Okay, so now step 2 in the FFT solution looks something like this. Sorry, moving some stuff around on my desk. Now we need to transform the PDE. Okay, and so basically, you take this partial differential equation, and then you take the inner product of both sides with a basis function. Another way that you can think about this is you multiply both sides of this equation by the basis function and integrate from 0 to 1. Okay, and so that's what we're going to do. It's going to at first look pretty similar to how this worked before. For instance, the left-hand side looks like this. Right, we start off with df dt, and then again we multiply that side by phi n, and then integrate from 0 to 1. Okay, and so just like before, you can interchange the order of differentiation integration. Right, and then this right here is just the inner product of f and phi n. So essentially what we have here, and so in other words, this is just fn of t, the coefficient, the nth coefficient in our sum. Okay, makes sense? Okay, right-hand side. Again, we have our initial term, d squared f dy squared times phi n dy. Okay, notice how here, I guess I didn't explicitly say this the last time we did this, but you cannot change the order of integration of and differentiation because it's the same variable, so that wouldn't make any sense, right? I mean, the derivative is with respect to y, the integral is also with respect to y, and so if you were to interchange something, then that wouldn't make any sense because, well, when you take an integral, you get one number, right? It's not in terms of y anymore, it's a definite integral, so you get one number, whatever the area is under that curve, and then if you take a derivative of that, then you just get 0, right? So that doesn't make any sense. Okay, so the way to solve this problem is to do integration by parts, right? And if you don't like integration by parts, or don't remember exactly how it works, or just aren't that comfortable with it, The answer is essentially the same every time. You can just look up what the answer is in the notes or in the textbook or something like that, right? It looks like this. That's a bad 0, sorry. That should be a 0. 0, there we go. Okay. And now it's a game of basically figuring out what each of these terms becomes, right? So, people start unmuting yourself. What is the value of this first term and why?
That's 0 because the basis functions are all 0 at the endpoints.
Exactly. This is 0 because of the basis functions. Okay, excellent. What about this one? Do you guys remember what happened to this term before? In the previous solution, what happened to this term?
Is it? I think it was 0. Was it 0 because the f is 0 at y equals 0 and y equals 1?
Exactly. That's what happened before, right? That's not true now, right? Because if you recall, before we were doing this in terms of G, and we actually broke up the steady state transient thing specifically so that we could get 0 basis functions, or sorry, specifically so that we get 0 boundary conditions, right? Our boundary conditions of earlier, I'm not going to scroll up. It's going to take me a while, and I'm going to lose our train of thought. But if you don't believe me, you can scroll up by yourself. The boundary conditions before said that G is equal to 0, and G is equal at y equals 0, and at y equals 1. Here, that's not true anymore. Okay. And so one of the boundary conditions is still equal to 0. That's okay. Okay. So at y equals 1, f is equal to 0. But at y equals 0, f is equal to 1. And so what we have is f is equal to 1 at y equals 0. Okay. And then the other term is 0, like I said, because f is equal to 0 there. Right? Now, what happens to this term? Last point where I'm going to ask you guys to unmute yourself. Anyone? Please? Do you guys remember what happened before for this term?
Don't you like take the two derivatives of the phi n and it turns into like what it was before, like the negative? So
Exactly.
You, like,
you take the two derivatives and it turns into what it was before, right? And so we can do that. It's the same as before, basically, right? And so if you don't remember, the answer looks something like this. If you don't believe me, we can look at it really quickly. You can actually evaluate the two derivatives of phi n, and that's taking two derivatives of this right here. If you take a derivative of sine, you get a cosine. If you take another derivative of cosine, you get a negative sine. And so that's where this negative comes from. The stuff on the inside has to come out twice because you took a derivative and chain rule. And so that's why you have an n squared right here. And then you basically just get what you started with before, phi n. Okay? And just to remind you, I won't write it here. I'll get to that in a second. The reason why we do this is because this is basically, again, the inner product of f and phi n. And so that gives us the actual coefficient f n of t. Okay? Now, as you guys can probably guess, the reason why we did not do this problem this way initially is because of this weird confusing thing right here where we have this term. Okay, but now we have enough experience to actually understand what's going on here, right? You can evaluate this. It's actually not that difficult. You know what the basis function is, so you can take one derivative of it and evaluate what it is at y equals 0. Okay, so let's do that real quick. The derivative of the basis function at y equals 0 is equal to, well, just the derivative of this, right? The derivative of sine is a cosine. So what I have is n pi square root of 2 cosine n pi y evaluated at y equals 0. And cosine of 0 is 1, and so therefore the value of that is n pi square root of 2. And so our right-hand side looks like this. That integral, again, where I multiply both sides by the basis function and then integrated from 0 to 1, gives me 0 plus this term right here, which, as I just showed right now, is equal to n pi squared root of 2 minus n pi squared times Fn of t. Okay, so to summarize, the overall PDE now looks like the left-hand side, which is this up here, equals the right-hand side. And just like before, we were able to transform our partial differential equation, our PDE, into an ODE. Okay? Because now we have, well, not one ODE, but infinitely many ODEs, but basically for the coefficients here, because all we have is just one derivative in time. So this is an ordinary differential equation that we can solve. Before we can do that, we have to do our step 3 of our FFT solution, because we need boundary conditions. Okay? So step 3 was transform the other PDE boundary conditions into boundary conditions for the ODE. Okay, and so we used boundary condition 1 and 2 in this case. That was what that weird term down here was, right? And so the only one we didn't use is this initial condition right here. Let me just rewrite that down here. The initial condition before was that at t equals 0, f is equal to 0. And so that implies a new initial condition that I'll call an IC prime. And that just says that Fn of 0, so Fn when t equal here, I'll write when t is equal to 0. If my pen were to work better, here we go. T is equal to 0 is equal to, well, the inner product of f and phi. Okay. And in this case, this is exceedingly easy because, well, my f at t equals 0 is equal to 0. And so the value of this integral is just equal to 0. So now we have one differential equation, or sorry, infinitely many, but you know, essentially one differential equation, an ODE, which has one derivative in time, and now we have one initial condition in time as well. And so we should be able to solve this differential equation. Okay. And that's the next step, right? Solve the ODE. And just for good measure, let me just rewrite exactly what the system here is. It's this first order linear differential equation. With an initial condition of okay. Does anyone know how to solve a differential equation like this? It's a first order linear differential equation. We've all taken a differential equations class at some point, maybe in college, right?
Integration factor?
Integrating factor, right? Does the word integrating factor ring a bell to any of you? Reach way back into your memory, I don't know, freshman, sophomore, junior class or something. I don't know when differential equations was offered in your undergrad, but you've almost certainly heard the term integrating factor. Okay, that applies for a first order linear differential equation. The integrating factor, this is not a differential equations class, although we are teaching you a lot of stuff about PDEs, but this is not a differential equations class. I trust that you can go back or just look on Wikipedia or the internet to sort of remind you guys how it works. The integrating factor in this case is e to the n pi squared t. Let me write that a little bigger, sorry. E to the n pi squared t. And I multiply the entire equation by that. Okay. Don't know if this looks familiar to you guys at all. Hopefully it does. The reason why we do this is that this allows us to collapse the left-hand side using the product rule, or the inverse of the product rule. Okay, because now the left-hand side of this equation looks like this. And of course, the right-hand side stays the same. Like that. And then therefore we can do one integral. So I'm going to integrate both sides. Sorry, this is not a minus. I don't know why I put a minus there. Okay. Now I can take the integral of both sides. So I get like that. And then can't forget our integration constant. And so then the overall solution looks like this. And of course, the integration constant comes in once we once we apply our boundary condition, okay? And so the initial condition, or IC prime in this case, implies that Fn of 0, which in this case is going to be square root of 2 n pi plus c, is equal to 0. That implies then that c is equal to minus the square root of 2 n pi. And so now we have our overall solution. Fn of t is equal to, I'm just going to simplify real quick. Like that. Okay, now that's just for f of n. The overall solution is, because we expressed our solution as a sum of basis functions with these coefficients, and so we basically just need to plug in our Fn of t in here. And then that's our solution. So let me just write out what the overall solution is. It's a sum over basis functions. Our basis functions were square root of 2 times sine of n pi y, and so I just multiplied the two square root of 2's together to give me this 2 right here. Okay? And that's our solution. As I mentioned, this is the second time that we've done this problem, right? We've actually done this problem before. Our previous solution looked something like this, where we solve for g of y of t, right? And if you recall, I'm just going to try and scroll up really quickly to try and find it. This was our g of y of t. Okay, so let me just rewrite that down here so that we can compare these two solutions. The previous solution looked like this. Right? This is just me copy pasting what was earlier. I just didn't want to circle and copy paste it. Okay, are these two solutions should be the same, right? Are they the same? They don't look like it, right? At least just not just, you know, staring at it very, very quickly. They actually are the same. Okay, you can see a lot of similarities, right? Maybe you guys will give me that. They both have this sort of e to the minus n squared pi squared t. They both have sine of n pi y and stuff like that. You could imagine that one way of rewriting this top solution here is by breaking it up. I could write this like this. Oh, sorry, I forgot my sine of n pi y. Okay. See what I did there? All I did was just distribute out this 2 over n pi times sine of n pi y into the sum. Okay, and so I actually have two sums here. So you can kind of see how these two terms look, how these two solutions look really similar, right? Both of them have this guy in the back over here. The only difference is on one of them I have a 1 minus y, and on the other one I have this. And I will tell you, not show you, but I'll tell you, and it's your job to show me, I guess. So maybe after the call or something, you can actually convince yourself that it's true, that these two things are equal. And the way you can do it is by noticing that all solutions or all functions can be written as a sum of basis functions. And so if you wanted to write the function 1 minus y as a sum of basis functions, this is what the result would be. Okay, so you can do inner products and stuff like that and show that the inner product of 1 minus y with our basis function looks something like this. Okay, play with that yourself. All right. But for now, I'll just say these two expressions pen is dying or slow or something are equal. Okay. Okay. On Wednesday, I promised that I was going to plot some of these things for you. And so let me actually plot that. How's this going to work? I'll share the overall screen instead of just my application. Okay, so I went ahead and wrote some code in MATLAB to do this. So hopefully there's a way for me to show you these things and have the MATLAB open. Okay, here were the two solutions. Okay. And so it's a sum like this, and so you basically have to, you know, write out everything, or you have to basically evaluate it in MATLAB. And the way you do it is basically you take, you actually calculate the sums and then you sum over them. Okay. So here's how you would actually do it. First, I'm going to give myself a set of x and t values. That's what xmesh and tmesh are using this simple command, mesh grid. Basically now, both xmesh and tmesh are two-dimensional arrays where, you know, each point in that two-dimensional array of X mesh gives me the X value of that array, and T mesh gives me the T value of that array. And that T is going to range from 0, or the X is going to range from 0 to 1, and the T is going to range from 0 to whatever T max I want. In this case, I just said 1. Okay. Okay. Now I also need N values. Okay. And so the N values, I'm just going to sum all the way up to 201, just because that's a really large number. Okay. I can make it smaller. We'll play with that in just a second. Okay. But for now, let's just do 201. Okay. And then I made another array that goes from 1 to 201, except now I'm going to make this in a third dimension. Okay, because I'm going to need to sum over all the terms, and so I'm going to sum over the third dimension. Okay, and so that's what these commands actually do. And then this sort of oh, sorry, I called this X, whereas in reality it's in our solution it's Y, but it's essentially the same thing. So pretend like X is Y here. Okay. So in here, in our solutions, every now and then I need to multiply n times y or x, and so I just pre-multiply that here. And then I also need to multiply n squared and t, and so I just pre-multiply that here. Okay, so in our previous solution, we use this sort of gn thing, and that's basically what this is. This as I highlighted right here is what's inside the sum. Agree? Right? 2 over n times pi times e to the minus pi squared n squared t, that's the n2t here, times sine of n pi y right here. Okay, and then it's MATLAB, and so if you're not familiar with MATLAB, I apologize, but you know, we'll use it every now and then in this class. You know that in MATLAB you have to put a lot of dots in there to multiply things element-wise. This sounds familiar, right? Not if you agree. Okay, cool. And then I went ahead and typed in the other one too. This is Fn of t. It's the same except this guy is in parentheses, and I have a 1 minus that. Okay, and then as I mentioned, I just have to sum over in the third dimension now. I have to sum over all of the n's. Okay, and so I'm going to do this twice. I'm first going to do it using the previous solution, so it's 1 minus y minus the sum, and then I'll do it again over here, and then the last stuff over here is just me plotting it. Okay, so it's a command called surf that gives me a surface plot, and then I label all the stuff and do a color map and stuff like that. Here we go. Okay, so here's what it looks like. Make that bigger. Okay, so you guys could hopefully have the drawing in front of you of like the schematic of what everything should look like, or picture what that should look like. At time t equals 0 over here, so along this line right here, along the y-axis, I guess, is when the fluid should be at rest. And so that's why the values are 0 down here, okay? And then at that time, suddenly the plate is pulled to the right at a speed of u. So in other words, the velocity suddenly becomes 1 at that point, okay? And then what we're seeing is the effect of that velocity increasing throughout the fluid, okay? And then by the time you get over on this side, you have basically a linear profile, a linear flow profile, because it's basically just simple shear between two plates. Okay, this sort of weirdness over here, like these sort of weird lines and stuff, those come about because of how I meshed my grid. I could make my grid a little finer, and those would probably go away. And then other things just to note, you see this sort of weird junk right here? That weird junk is because it's an infinite sum, and in MATLAB I can't actually evaluate an infinite sum. Okay, and so the infinite sum is a particularly poor approximation at this point right here, specifically because the solution actually jumps discontinuously between these two boundary conditions. If you think about it, at the moment that the plate is pulled to the right, you know, you have to simultaneously satisfy the 0 initial condition where the fluid flow is 0 and a no slip condition where the fluid flow is equal to u at that point. And so that's why at the point y equals 0 and t equals 0, it's a particularly bad solution. And so you can see these sorts of weird oscillations where basically the basis functions are trying to make it work at that point. Okay, I can show you exactly what the other solution looks like. And so what I'm going to do is take this out or uncomment that and then comment this guy. And so it looks essentially the same. Again, you see weirdness happening like on the edges, close to a boundary and stuff because of these weird things with boundary conditions and discontinuities and stuff. But you know, the overall solution looks exactly the same as before. Okay. And so in the homework, what I might ask you to do is like plot a few slices of this surface plot, for instance, right? Like what does the fluid flow profile look like at a time t equals 0.1 or time t equals 0.5 or something? Not for this particular problem because we already did it, but for whatever problem that the actual homework is. Okay. Just to show you, here I used 200 terms. If I had done a much smaller number of terms, let's say 11 terms or something like that, and let me go down to here and go with my original thing. You can see it's actually an even worse approximation, right? This is what I mean when I say these discontinuities become like a relatively large, an even larger issue. This is where you have these issues, and my MATLAB is slow. I apologize. I'm trying to be able to rotate it so I can show you guys. The overall solution, kind of far away from this initial point, is actually not bad. You see that it eventually does approach this linear profile, which is exactly what you'd expect. Again, simple shear between two plates on this left-hand side right here. But this initial thing right here comes about because, well, essentially our solution is a sum of basis functions, and our basis functions are sine functions. And so I'm just basically trying to add together a lot of sine functions to get something that looks flat, and that doesn't always work out as well as I would hope. Okay, make sense to you guys? I have about 15 minutes. I'm going to move on. Let me go back to sharing the actual notes. As I keep talking about, the magic of this whole thing comes about from the basis functions. Okay, here we're using basis functions that's equal to square root of 2 sine n pi y. That's not necessarily always going to be true. Okay, as I mentioned, the boundary conditions could change, and also the partial differential equation could change too. You can imagine, you know, this was our original partial differential equation. Right here, df dt equals d squared f dy squared, but it could totally be a little bit more complicated than this, right? And so that would imply that we instead of solving a problem that looks like this, it might be a more complicated problem or something. In fact, here's where we were talking about the basis functions, right? And you know, the three requirements for the basis functions, if you recall, is that they have to satisfy this eigenvalue problem, which allowed us to do that thing that on the last term of the integration by parts, where you took two derivatives of it and it became itself again, right? It also has to satisfy boundary conditions of the same type, and so that's what allowed one of those integration by parts terms to turn into 0, right? We talked about that a little bit earlier in this lecture as well. And they also have to be orthonormal, right? And so the way we figured out what the basis functions were is basically we satisfied these conditions by force, basically, right? We actually wrote down this differential equation and solved it and applied the actual boundary conditions that we wanted and solved it. But what we have not talked about is that how those basis functions actually just became orthogonal. In this case, I asked you to sort of take my word for it, and then maybe some of you guys went home and then typed a few integrals into Mathematica and then showed yourself and then convinced yourself this is actually true. It turns out that in this class of problems, these functions are always going to be orthogonal, and I'm going to show you a little bit why. And while we do that, I'm also going to show you how to deal with more complicated problems. And the way to do that is using a framework called Sturm-Liouville theory. Okay, and the question I'm going to start off with is basically, what if the problem is more complex than this for the basis functions? Okay. The operator that I was talking about, the second order operator, is actually more general than that. the general operator is, and this is going to look really complicated initially, but I'll show you that in practice it's actually never nearly this complicated. The general operator looks like this. Okay, this is just a differential operator. In other words, what it does is for any function, if you were to take this operator on that function, then you multiply it by q of x, or actually what I'll say is you take a derivative, you multiply that derivative by some function p of x, then you take another derivative of that, and then you also add the product of that function with the q of x and then divide the whole thing by w of x. Okay, all these things have a particular meaning, but I'll explain that in a second. Okay, and then our basis functions then become solutions to this equation. Sort of like how this was the solution to our basis functions in the simplest case right here. Okay. To write out the actual equation that we would solve, to make sure there's no ambiguity for how to actually apply this operator, the equation that we would solve to find our basis functions would look something like this. Okay. This left-hand side is basically just applying this operator L sub x to phi. Okay. And just like before, this has two boundary conditions. Those two boundary conditions are either phi equals 0 or d phi dx equals 0. These were called the Dirichlet conditions. These were called the Neumann conditions. Or you could have mixed conditions. We will likely not have any mixed condition cases in this class, but this sort of stuff comes about if you have like a Newton's law of cooling or something in heat and mass. Okay. And the two boundary conditions are this, this, or this. That's valid at either x equals 0 or x equals 1 or something like that. Okay, and again, you can have one of each. You could have like phi is equal to 0 at x equals 0, and then d phi dx is equal to 0 at x equals 1, or something like that. Okay. When you have a problem like this, the inner product is basically what makes the whole basis function stuff work. That is defined as this. The inner product of two functions, f and g, is again defined as what happens if you were to multiply the two functions together and integrate, except now we have another function, w of x, and this w of x is the same w that I have up here. Okay, so the inner product is the same thing, it's just you have to worry about this additional thing that you have to add in right here. Okay. So just to ground this really complicated framework into something that we already know, this was what we've been playing with so far, right? Because our differential operator was just d squared dy squared. Okay, and so our previous problems were a special case. Or a special case where p of x is equal to 1, q of x is equal to 0, and w of x is also equal to 1. Okay. When those function definitions are true, then you could imagine this equation here reduces down significantly, right? Thus, previously, we've had L sub x looks like, well, 1 over 1 is just 1, right? And then p of x is just equal to 1, and so this is just a second derivative. It's just taking two derivatives, and then q of x equal to 0. And so that's how our previous operator just looked like this. Okay. And then, of course, our inner product. Sorry, I should have a little bit of a space in between there. Our inner product was just, you take the two functions, you multiply them together, and then you integrate. Okay. Now, a kind of cool property in the general case. So in general, a cool property about this operator is that it is self-adjoint. Okay. I'll explain to you guys what this means. What that means is that if you have two functions, f and g, this means given any two functions, f and g, then this relationship is true. I'm not going to prove to you, sorry, that should be a bracket. I'm not going to prove to you that this is true, but you can show this just using integration by parts. Okay, you can basically just write down this operator applied to f, try and take an inner product with g, and then use integration by parts to simplify it, and then you'll arrive at this guy on the right hand side here. Okay, so I'll just say can show using integration by parts. Okay, and also in general, Lx of phi, so again, this operator applied to some sort of function, to some basis functions, is equal to this. Remember, this is the equation that we solve to get our basis functions. Has infinitely many solutions. And we call those eigenfunctions. And those eigenfunctions are basically the same thing as our basis functions. And they each with an eigenvalue lambda n. Okay? Okay.
Rachel?
Yeah.
But just to make sure, the fx and gx here are both have to be the solution for the original equation, or?
No, they don't. They can be any solution, or they can be any functions.
So the inner product definition has the wx in
Exactly.
it.
Yep.
So each of that operator is defined for under the context of the ODE?
Yeah, so another way of writing this guy right here is saying that this equation is true, is that this is equal to this. Okay. And just to be clear, this guy right here is one function, and this guy is another function. So to evaluate these integrals, you first take this operator and apply it to whatever function g of x. And so if you wanted to show this, you can imagine then applying this operator as written into here, and then performing integration by parts, and you'll eventually arrive at this thing on the right. Okay? Now, these properties of this operator, the fact that it's self-adjoint, actually gives us some cool effects. I'll say because Lx, that looked like LT, sorry, Lx is self-adjoint. Okay. Then let's say we have two eigenfunctions. So in this case, we have two functions that actually do satisfy this equation right here. Okay. Then this has to be true. Sorry. That's supposed to be erased. For two eigenfunctions, phi n and phi m. Okay. That's basically just, well, what happens if we let f here equal phi n and g equal phi m, right? But because these are eigenfunctions to this, or these are solutions to this equation, then we can simplify the left-hand side. Okay. And we can also simplify the right-hand side. Okay. This gives us the eigenvalues for each of them. To give you something a little bit more concrete, the eigenfunctions and the basis functions that we were talking about earlier were like sine of n pi y, right? And the eigenvalues of each of those were n pi. Okay, if that rings a bell at all earlier. Now, what this implies then is, well, I can move this to the left-hand side of the equation, and this over here is just a constant, right? Lambda n is just a constant. And so I should be able to pull that out of my inner product. My inner product is just an integral, and so I should be able to just pull a constant outside of the integral, right? And so this implies that. Okay. And so what this means is that because lambda n does not necessarily equal to lambda n for n does not equal to m, then that means that the inner product has to equal 0. Okay. That implies this key property of the inner product, that eigenfunctions or basis functions are orthogonal, right? This was how we were able to do all of the whole FFT stuff, if you will, right? The FFT stuff was all based on the fact that the inner product allows you to becomes the Kronecker delta, and so you can apply this Kronecker delta property to then pick out individual coefficients of that sum and then solve for individual coefficients, right? And so this implies that eigenfunctions or basis functions are orthogonal. Okay, and this is not just true for the particular case of sine n pi y that we played with up here. You know, well, that we played with up here. Okay, you know, in this case, you can go in and like I said, just go into Mathematica and type in a few of these integrals and maybe convince yourself that it is equal to 0 if n does not equal m, right? In this case, for a much more complicated problem, you can still use FFT. Okay, and we just mathematically proved that right now. And so, just to summarize real quick, then.
Sorry, why is there why is it lambda squared m instead of negative lambda squared.
Sorry, say that again.
So for the when you did exchanging the operator to the eigenvalue.
Oh yeah, that's just because I messed up. Okay. Okay. So how does this relate to PDEs and FFT? Okay. In general, our PDEs look like this. Right? In our particular case, our operator here was just d squared f dx squared. But you could imagine more complicated ones. And on Monday, we're going to talk about a more complicated operator. Okay? And the way we do FFT is we solve by transforming both sides. If you recall, the inner product on the left-hand side was easy. That just looked like that. Okay. The right-hand side, you have to use integration by parts. And the integration by parts here is a little bit more complicated, but it's the same every time, and so I'm just going to write out what this looks like. And I'm doing the limits from A to B rather than 0 to 1, just to be a little bit more general. Okay, this is what you would get if you were to apply integration by parts to this inner product integral. Okay, and then of course, the reason why we do this is because we can use some of our boundary conditions here to get rid of some of these terms or simplify some of these terms, right? Boundary conditions for both the basis functions and for the original problem. And then of course, this guy right here, we can use our equation for the basis functions right here, right? Our equation here for the basis functions to simplify this. This is where, as we mentioned a little bit earlier, you know, if you just take two derivatives of this, then you happen to come up with what you had originally. And so this becomes something like that. And then this over here, you can pull the negative lambda n squared out, and then this just gives us the inner product of f and phi. And so this is just, sorry, this is just that. Okay. And so that's in general how we solve FFT problems, if they're a little bit more complicated than what we happen to do right now. Okay. All right. Happy Friday. Oh, sorry, I'm just a couple minutes over. Hopefully I didn't break any of your plans. Any questions at all about this?
Is someone else asking a question?
Oh, all I was going to mention is on Monday, I'm going to talk about the more complicated case for this. You can imagine maybe scenarios where the PDE looks a little bit more complicated than just df dt equals d squared f dx squared, for instance. And then there's another example that I sometimes do in class. We didn't end up getting to that because of like how compressed things are and stuff like that. But either me or the TAs are probably going to cover that example during one of the upcoming office hours and stuff. And that might show you some other scenarios of what might happen in an FFT problem. Okay. Nikhil, did you have a question?
Yeah, like I was just gonna ask, like the only reason we're able to make this work is because we're effectively linearizing PDE, right? Like this shouldn't work for nonlinear systems, right?
This does not work for nonlinear systems, no. All of the PDEs that we've been doing so far, in fact, all of the flow problems that we've been doing so far have all been problems where the fluid always moves in one direction and moves slowly enough that we don't have to worry about any of those inertial terms. Okay. And so once we cover this stuff and there's like one other thing, then we're actually going to start to talk about like non-unidirectional flows and things where inertia matters and all of that fun stuff. But we're sort of doing the simplest case of flow problems, and you can already see how complicated it gets when we try and do that. Any other questions?
Mitchell, how did you get from the second to last line to the last line?
How did I get from this line to this line?
Yeah.
Yeah, so here I pulled out a negative lambda n squared in front. Okay. And then what I'm left with then is f of x phi n wx, and that's just the inner product of f and phi n.
Oh, okay.
Because inner product here is defined as you multiply the two functions together and multiply by w of x. Just so you guys know, this w of x is sometimes called the weighting function. Weighting function I can write like this. And to give you a little bit of a preview, that weighting function, it's kind of like how in cylindrical coordinates, you always have an r in the front of the dr, right? Or in like spherical coordinates, you always have like an r squared sine theta. That's what that weighting function actually is. That's where it's going to come up when we talk about this on Monday. Okay.
Thanks.
Mm-hmm.
Also, I think given that I think a few of us have like 2 tests on Wednesday next week, would it be possible to just have the fluid or the homework be due Friday instead of Wednesday so that we can take
How
them?
does everyone feel about that? We probably are not going to move office hours. Hopefully you guys should be able to handle that. But I'm okay with that. We can just declare that right now. Okay, cool. Homework 5, right? Yeah, is now due on Friday.
I also think Jenny had a question. It was in the chat.
Oh, did I not see a chat? I'm sorry. Chat. When is it going to be decided when the midterm is going to be? Please respond to the poll in the next 24 hours, and then I'll talk to the TAs and stuff, and we'll announce it soon. Like I mentioned, it'll probably be at some point. It'll probably be at some point in the evening. Okay. All right. Thanks, everyone. Have a good weekend. I will post the MATLAB script on Canvas. Yes.
Thanks. Have a good weekend.
See ya.